So in this video, we're going to review really everything about quadratic functions. So this is kind of a quick review. If you've learned this before, maybe you're like a pre-calc student or a calc student or an algebra student looking to review. Okay, so before I can talk about a quadratic function, I just want to remind you what a polynomial function is. So the definition, the mathematical definition of a polynomial function has this really wild definition. It looks really wild. So it's f of x equals this a sub n, x to the n, a sub n minus 1, x to the n minus 1, all the way down to a sub 1 plus x sub 0. So I know this looks really, really crazy, but basically what this is trying to say, like the reason that this is so long, polynomials can have whatever exponent you want as long as it's a positive whole number. So I could have a polynomial starting at like x to the 100th, and then x to the 99th, and then x to the 98th, and go all the way down to x squared, x, and then a number. So polynomials can be as long as you want, really. So what does the rest of this notation mean? Just as a quick reminder, these a's, this is a sub n minus 1, a sub 1, a sub 0, those all stand for numbers. Complex numbers, real numbers, whatever type of number you want. And then these n's are going to be integers, but they have to be greater than 0. So I'll show you a couple of polynomials in a moment just to kind of refresh your memory. But the highest exponent that you see in a polynomial is called the degree. Just a reminder, the degree of a polynomial is the highest exponent. And the number in front of that highest exponent is called the leading coefficient. So these things get referred to a lot when you talk about quadratics, so it's just important to review that. And then this entire thing here is known as the dominating term, so the leading coefficient with the x to the highest power. So just to like really briefly kind of remind you, how does this work? So I have a few examples here. Okay, so I want to find the degree, leading coefficient, and dominating term. So I intentionally wrote this first polynomial out of order. So normally when we write polynomials, we want the highest exponent to go first and then go down in descending order. So as I look through these exponents, the highest exponent is right here, x to the 7th. So whatever the highest exponent is, that is the degree of your polynomial. And then for x to the 7th, whatever number is in front of this, which we don't have one, so we assume it's a 1, that is the leading coefficient. And so then what makes the dominating term? It is the entirety of the leading coefficient with the x and the exponent. So in this case, it would just be x to the 7th as the dominating term. Now, for b here, so I've got x times the square root of 3 minus 5. So something weird with square roots, like a common convention, is that we often, like sometimes you can see them written after the x. It's just because like that notation, sometimes it's hard to read, like square root of 3 times x. It can be difficult for your eyes to see that this bar is not supposed to go over the x. So we flip the order when we work with square roots. But I partially wrote this example just to remind you, you can have whatever weird numbers you want for coefficients. Just so long as your exponents are whole positive numbers, that is all that really matters. So when I look across here, the highest exponent is actually the one that we can't see. It's what's right here. So we assume that that exponent is 1, so this is a degree 1 polynomial. And then the leading coefficient is whatever number. Now normally, we would want this in front, but in this case this one is behind. But the number that is attached to the x is a square root of 3. So the dominating term is x square root of 3. And then finally, just to mention this, so what about just having a number? So a number is actually just a plain old number is considered to also be a polynomial. It is considered, when you talk about the degree, it is considered to be a degree 0 polynomial, where both the leading coefficient and the dominating term will just be the same thing. Now, a quadratic is a certain type of polynomial. Quadratics refer to polynomials that are just always degree 2. We just know this. They are degree 2 polynomials, full stop. And the graph of a quadratic is called a parabola. So just to remind you of what the parabola looks like, I've talked about this in some other videos, but parabolas, so they can open up, they can open down. The highest or lowest point are known as the vertex, and then there's an invisible line that technically cuts through that parabola perfectly, and then it's symmetric on both sides. That's known as the axis of symmetry. So I've talked about this in some other videos, but just like really briefly to kind of refresh your memory, if you've been going through my series, then this should be familiar to you. How would I graph this particular parabola? Well, if you've been watching my series, I would recommend that maybe you pause here and just check your understanding and then hit play when you're ready. So this is just, I assume that you kind of know your graphing techniques. So if what I'm about to say just kind of goes over your head, I have a whole other set of videos where I explain how to read these types of equations. So if you're watching this, feel free to check out one of those videos. I'll drop some links in the description. Okay, so decoding this function. So this is a degree 2 polynomial. I see that right here, so I know it's quadratic. Now, this negative here means that I need to reflect over the x-axis. This +4 means that I move 4 units left. And then this -2 means I need to move my vertex 2 units down. Okay, and then there's no stretch or shrink factor, which makes this a lot easier. So the first thing that I'm going to do is I'm going to move the vertex 1, 2, 3, 4 units left and 2 units down. So here's where my vertex is going to start. Now, this is a polynomial that's actually going to open, so we can think of it as reflecting over the x-axis, or we can think of it as opening down. So I know, and I've talked about this in other videos, of how when I draw the vertex, how the other points for the parabola relate to one another. So to get to the other 2 points, I'm going to go out 1 and down 1 in each direction. And I go down because I have the negative there, and that's what gets me that reflection. Okay, and so there is my parabola. So that's something we've talked about in other videos, so it shouldn't be too surprising. But something I want to talk about that is specific to parabolas is this form of the equation. So you've been working with this form of the equation without really thinking of it, but we have a name. This is the vertex form of a parabola. And so it looks like this. A is some number, x minus h squared plus k. So hk, what we've been saying, how the vertex moves, this is actually what the vertex is, hk. And then that axis of symmetry is just x equals h. So whatever your h is, you can just set that equal to your axis of symmetry. One thing I just want to point out here, x equals h. The axis of symmetry, it is an equation. It's not just a number. If you just write one number without the equation, you're not going to get it right. You need that x equals as part of it. Okay, so a thing that we have to deal with is that if you think about it, when I showed you the initial just definition of a quadratic function, so think about this. This is not in vertex form, right? So this is the standard form of a quadratic function, but it's not in a nice graphing form. It is not similar to this. This I can graph very easily. The first one I can't so much. So the question is, what do I do if I have something in this standard form? How can I put this into vertex form? And the answer is that you use completing the square. So I'm going to show you how to do that. So, okay, I'll give you some directions. So this is what I think is kind of weird, but I think I teach this a little differently than like a lot of books do. I like to isolate the x variables to one side, and this is going to make this look a little odd. So what I'm going to do is I'm going to add, I've got the f of x, and I'm going to add a 4 to it right now. So what's weird about this is usually when we see f of x, it's not like we add something over to the other side. But for now, I'm going to do this just as a placeholder. I will sort this out again later, but I feel like going this technique, it aligns more with like how completing the square is kind of taught versus a lot of books. I feel like they kind of add some extra steps that I think it just gets hard to remember. So I try to just make sure I teach the same thing kind of in the same way over and over. So the next thing that I want to do is I want to work on completing the square on the x variables. So let me write that down. So I want to complete the square. And so what that means then is I kick off the process of finding what my b is. Now, b is considered to be whatever is attached to the x. So in this case, my b would be 6. So once I identify that b, that really kicks off the rest of this process. The next thing that I do is I find half b, which is equal to 3, and then I square that result. So half b squared, or 3 squared, is equal to 9. Then, to continue with completing the square, this is all a part of completing the square, I'm going to add that 9 to both sides of the equation. Okay, so let me see if I can write this all in one line. So to now simplify kind of where I'm at, I now have f of x plus 13 equals x squared plus 6x plus 9. Okay, so let me clear a little space. And now I can do the completing the square part, which is I can write this side as a perfect square trinomial. So this becomes f of x plus 13 equals x plus 3 squared. If you're ever confused as to what you need to factor, the x plus, what you put here is always whatever your half b is, by the way. Okay, so now I have completed the square, and the last thing that I need to do now is I need to, so let me just write this down. So the last thing that you want to do now is kind of undo the thing that feels weird in this. So I've got this f of x plus 13. Like I said, we don't usually want to have f of x like plus something. So this side is kind of just a placeholder, and then we unravel it by just solving for f of x again. So I have f of x equals now x plus 3 squared minus 13. And so look what I've done now. I have put this equation into that graphing form. We know what type of parabola this is, right? This is a parabola that will open up, and it's going to move 3 left and down 13. So that is how you can transform a parabola. So I want to do this one more time now with a slightly more complicated example, just to show you how crazy this can get. So I've got f of x equals 3x squared plus 5x plus 2. Okay, so what I'm going to do is, in this case, so let me add one more direction. So the one other caveat that I want to throw into this is if your leading coefficient is not 1, which in this case it's not 1, it's 3, when that happens, then you need to divide by whatever that leading coefficient is so that you can force the right coefficient. So what I mean is I have this f of x equals 3x squared plus 5x plus 2. So I'm going to go through, I'm going to divide every single part of this by 3. And so this is going to be a much messier equation. So let me make some room. And then let's just write out what we're left with. So I'm going to write everything in terms of fractions. I think it's just a little more visually appealing. So I have 1/3 f of x equals x squared plus 5 over 3x plus 2/3. Okay, so now we can go ahead and do the same completing the square process. So to walk you through this, this means that first I want to get these two x's by themselves. So I'm going to subtract off the 2/3. So I'm going to have 1/3 f of x minus 2/3 equals x squared plus 5 over 3x. And now I can go through the steps to complete the square. So my b in this case, I look for the x and whatever is attached to that. So in this case, that would be 5/3. So we've got 5/3, and then what is my half b? If you're having trouble figuring out what half b would be because you have a fraction, then just do the multiplication somewhere on the side. So if I take 1/2 times 5/3, so remember, I just multiply straight across. 1 times 5 is 5, 2 times 3 is 6. So half b is 5 over 6. And then finally, what is my half b squared? I square the top. 5 squared is 25. I square the bottom. 6 squared is 36. And now, so we're still following the same steps from before. In completing the square, I want to add this 25 over 36 to both sides. So this definitely looks a little gnarly, but we're going to keep going with it. So I've got 1/3 f of x minus 2/3, and then I'm going to add that, let's see, maybe I'll do this in pink so you can see it, plus 25 over 36. And then this is x squared plus 5/3 x. Let's see, I'm kind of running out of room. Let me just maybe write my half b squared 25 over 36. I'll just write it over here so I can make some space for myself. Okay, and so then I'm just going to add 25 over 36. Okay, so This looks a little gnarly, so let me clear some space. So the good news is that because we have all of this information about completing the square, even though it looks really gnarly, it's not too bad. The one thing that we do have to do is we have to simplify this fraction here. So if I just write this out, so maybe I'll just write this out on the side, negative 2/3 plus 25 over 36. So I've got to turn negative 2/3 into a common denominator. So the common denominator here will be 36. So I need to multiply the top and bottom here by 12 over 12. So let's see, 12 over 12. So that this set of fractions becomes negative 24 over 36 plus 25 over 36. And so if I add those together, that becomes 1 over 36. So now I can rewrite this as 1/3 f of x plus 1 over 36. So that's the left side. And now we have to factor this side. Now, if you're panicking about the factoring, remember I told you that there was a little bit of a roadmap, right? So this, I don't even have to think about too hard about how it factors. This is just going to be x plus what? So think about what I was just saying. If you look in this, this is a little bit of a roadmap. This is going to be x plus whatever your 1/2 b, so in this case 5/6, it's whatever your 1/2 b is. So you don't have to like panic about, I can't figure out how it factors. No, you actually figured it out already. It's in that roadmap. So now look at where we're at. We've got all of this information. So let me clear a little more space. So we've completed the square, and now remember we have to solve for f of x. So I've got this 1/3 f of x plus 136. So first I'm going to subtract off the 136. So I've got 1/3 f of x equals x plus 5 over 6 squared minus 1 over 36. So the last thing I need to do now is I need to get rid of this fraction. So to get rid of this fraction, I want to multiply this side by 3, and then I have to multiply each part of this equation by 3, and this is the part that gets everybody. This part has to be multiplied by 3, as does this part. So you have to multiply by 3 times in this case. And so then I'm left with f of x equals 3 times x plus 5/6 squared minus 1/12. Woo! Okay, so we got it into vertex form. And so once again, this I can now actually graph. Now it will be a little gnarly because it'll be, you know, negative 5/6 and negative 1/12 as the vertex, and then it's also got this stretching factor, but we could totally do it, right? And so that is how you approach vertex form if you have kind of crazier numbers, if you will. Okay, so just a couple other things I want to talk about here. So sometimes when you're working with quadratics, you will be asked to find intercepts. So there are two ways you can find the intercepts. So first, to find the y-intercepts, that is always the easier side with these. So you can just plug 0 in, and so in this case I get 2. So my y-intercept in this case is 0, 2. So just plug 0 in and you're good to go. Now, the slightly harder thing that comes up with these types of equations is the x-intercepts. And so for those, you have to take your equation and set it equal to 0. And then this is a quadratic, so you just have to think of all the different ways that you know how to solve a quadratic. So any method goes. Now in this particular case, we can use factoring, but I'll warn you, it is totally possible that you would have to use like the quadratic formula, completing the square root property. So just be on your toes, stay on your toes when you're trying to solve for x-intercepts. So in this case, I can factor this as, let's see, how does this factor? 3x plus 2, x plus 1. Okay, I figured it out. So I have two x-intercepts. My first x-intercept is, let's see, my solutions in this case would be x equals negative 2 over 3 and x equals negative 1. Those are the solutions, but these are not x-intercepts. An x-intercept is a point. So I'd write this as negative 2/3, 0 and negative 1, 0. So those are your two x-intercepts in this case. So set it equal to 0, see what you get. Now, something I do want to mention, how many x-intercepts can a parabola have? There's actually three possibilities. So like we just found in the example, it's possible that a parabola could have two x-intercepts, and that would be a situation like this. It could open up or down, but it's going to intersect twice. You could also have that a parabola has only one x-intercept, which would mean that only the vertex touches the x-axis. So this would be one x-intercept. And it's also possible for a parabola to have zero x-intercepts like you see here. So it just doesn't cross the x-axis at all. That's totally fine if that happens too. So the question is then, how do you know how many x-intercepts does a quadratic have? So if you are looking for a way to double check yourself on that, what you can do is you can calculate this b squared minus 4ac. So you look at your equation, you choose out the a, b, and c, and you calculate this. You might remember that this is also known as the discriminant. So depending on what your answer is, if you calculate this and it's greater than 0, you're guaranteed to have two x-intercepts. If you calculate this b squared minus 4ac and it equals 0, you're guaranteed to have one x-intercept. And if your b squared minus 4ac comes out to something less than 0, then you won't have any x-intercepts. So this is just a second way that you can check yourself. The last thing that I want to talk about in this crash course review of everything with quadratics is the vertex formula. So you can find the vertex, of course, if your parabola is in vertex form. But what if you're trying to find the vertex and I have this standard form? So an alternative way to figure out the vertex without having to go through all the work of completing the square is to use this vertex formula. So you identify what the b and the a are. You take negative b over 2a like you see here, and then you just plug that back into the function to find the vertex. So let me show you how that works. So let's say I want to find the vertex of f of x equals 2x squared minus 4x plus 1. Okay, so in this case, what's in my a position? It would be a 2, and what's in my b position? It would be a negative 4. So what I want to do first is I want to calculate negative b over 2a. So this becomes negative 4 over 2 times 2. See how all of that works? And so this will just equal really 4 over 4, which equals 1. That's the first part of this. Now you want to take that 1 and you want to plug it into the function. So then I just plug it in like you see here. And this becomes 2 minus 4 plus 1. So let's see, that's going to be negative 1. So my vertex then is the point 1, negative 1. That's an alternative way to find the vertex if you don't want to go through all the work of completing the square. Okay, so like I said, this is really just like a crash course review to remind you of everything with quadratics. There's a lot of stuff to talk about with quadratics, so I had to kind of cut down the number of examples. If there's anything in this video that you wish you could see more detail on, don't worry, I have entire series on all of the topics that I reviewed here, so I'll drop links to them in the description. But that covers your crash course review of important things about parabolas and quadratics. I'll catch you guys in the next video.